Welcome back, everyone, to another college algebra lecture. Today, we are going to start talking about how you can solve exponential and logarithmic equations. Now, in our lecture dealing with exponential functions, we have already talked about how you can solve some exponential equations. But in this lecture, I'm going to expand on those that we've already talked about and how you can solve new types of exponential equations. But before we get into exponentials, let's start on logarithms because they're a little bit more straightforward in certain cases. And our properties for logarithms can help us out with our exponential equations later. All right, so to start with, the type of logarithmic equations we're going to do are equations that contain only logarithmic terms. So what I mean by that is, looking at these two examples, have a logarithm equal to another logarithm. Now, there is a property that says that if you have a log equal to another log, as long as they have the same base, then the insides will be equal to each other. Now, the converse of this one is true also. If you have two things that are equal, you can take the log of both sides. That's something that's going to be really useful for us on the last page of today's notes. But to start with, we just got to make sure that we have two logs equal to each other with the same exact base. So the bases being the same is important. Okay, so starting off on the first problem, I notice that we have log base 3 of 2x minus 1 equals log base 3 of x plus 5. Here, I have log base 3 equals log base 3. Since those are equal, I can set the two insides equal to each other. That means I have 2x minus 1 equals x plus 5. Pretty straightforward. All I have to do, make sure the logs are the same. Now I can go through and solve. I'll subtract the x, I get x. I'll add the 1, I get 6. We found our variable. But this is where the only catch on these type of problems is. You have to make sure you check for extraneous solutions. During our discussion about logs, we know that the inside cannot be a negative or a 0. So that means that the inside of each of these has to be greater than 0. Well, to see if the solution is extraneous or not, all we have to do is just simply plug it in and see if it makes the inside negative or 0. So taking the 6 up here, 2 times 6 is 12, minus 1, that's 11, positive number, we're good over here. Now for the 6 going into this one, 6 plus 5 is positive 11. So this truly is an answer that works out for us. All right, that's it. That's all you gotta do. Make sure the logs are the same, set the insides equal and solve for x, then make sure that the variable that you solve for doesn't make the inside less than 0 or equal to 0. All right, let's do it again. So looking at this next one here, I see I have natural log equals natural log. Since they are the same exact thing, I have x squared minus 15 equals 2x. Okay, well at this point, I see that this is quadratic, so I need to move that over. That gives me x squared minus 2x minus 15 equals 0. Now I can factor this. Factoring it, I see that I'm going to need to use, let's see here, 3 and 5, and the 5 needs to be negative. Got it. Solving, this is going to give me negative 3, and that's going to give me 5. Now again, you have to make sure that when you substitute these in, you do not get a negative or a 0. So I suggest always looking at the small one first because it's less work to do. If I substitute negative 3 in up here, 2 times negative 3 is negative 6. That gives me a negative number. I cannot have that. So showing a little work on this, 2 times negative 3, that's log of negative 6. That is not allowed. So that's not a solution for us. Now checking 5, 2 times 5 is 10, positive number, we're good. Here, 5 squared is 25, minus 15, that's a positive number, we're still good. So be very careful. Always substitute the number in and see if it gives you a positive number. All right, now if you're good after that one, feel free to skip ahead, but I got a couple more examples to kind of help you out. Looking at this one right here, I see I have log equals log. That means I can say that I have 8x plus 5 equals 5x minus 16. Solving it, I can move the 5x over, that gives me 3. I can move the 5 over, that gives me negative 21. Divide by the 3, and we get negative 7. Okay, so at this point, I have to check it out. And when I check it, I'm just going to start with this one right here. So I have log 8 times negative 7 plus 5. Well, 8 times negative 7 is 56, plus 5 is negative 51. That's a negative on the inside. That does not work. So this one has no solution, or the solution set is empty. That's all you got to do. Okay, now one more. And for this one, same situation. Log 4 equals log 4. So I have x squared minus 2x equals 24. This is quadratic, so I'm going to move the 24 over. Now, factoring this one, let's see here. I'm going to need to use 4 and 6, and the 4 will be positive and the 6 will be negative. Got it. So that gives me x equals negative 4 and x equals 6. Now, here, based on our two examples previous, you might be very tempted to say, this one's not going to work because it's a negative x. But you always have to plug them in and see. So plugging this one in, there's no x over here, so I'll only look at that side. Negative 4 squared is 16. Negative 2 times negative 4 is 8. 16 plus 8 is 24. This one worked out just fine. Now when I check this one, that's going to give me 36 minus 12. That's 24. It works out fine also. So both of these work. So do not fall into the trap of thinking just because the x is negative, it doesn't work. All right, so these are the most straightforward and basic logarithmic equations that you can solve. Now let's see what happens if you do not have every term with a logarithm. All right, so on this page, we're going to look at equations where you do not have a log around every term. So what I mean by that, looking at this first one, there's log of 5x, but the 6 doesn't have a log and the 3 doesn't have a log. Well, if everything doesn't have a log, I cannot use the property on our previous page. I can't set the n sides equal. So in that case, I gave you some steps on how to solve it. What we're going to do is we are going to combine and or isolate the logarithm by itself if possible. Then we are going to change it into an exponential. All right, so changing logarithms to exponentials, I gave you the little reminder over here. Y equals a to the x power if and only if log base a of y equals x. This is what we can use to convert between them. All right, and anytime I say isolate the logarithm, if possible, I want this log, including what's on the inside, to be on a side by itself. So to start on this problem, I'm going to isolate the log by adding the 6 to the other side. That's going to give me log of 5x equals 3. Now that the log is on a side by itself, I'm going to convert it over to an exponential. And this is something we did do last time. Now, before I start converting, I need to take note that this is log. There's no number under it. So any time that we have that, log of x is equal to log base 10 of x. You need to remember that. And while we're at it, if I give you natural log of x, that means log base e of x. So when I convert this, I see that the inside is going to be on a side by itself. So I have 5x equals, now the base is going to be the base of the exponent. So I'll have base 10. And this 3 is now the exponent. That's how we can convert between log and exponential. Now simplifying this, 10 to the third power, that is equal to 1,000. Now I need to divide this by 5. So dividing this by 5, give me a second. My mental math isn't so sharp right now. I get 200. All done. Now, check for extraneous solutions still. So if I substitute this 200 in for x right here, I still get a positive number. So everything's nice and dandy. That's it. That's all you got to do. Isolate the exponential by itself, then convert it to, or isolate the log by itself, then convert to an exponential, then solve for x. All right, so let's do it again. Looking at this one right here, the log, including everything in it, needs to be by itself, so I have to get rid of this 2 out front. So dividing both sides by 2, I now have log base 4 x squared plus 6x equals 2. Now that it's on a side by itself, I'm going to convert back to an exponential. So I know x squared plus 6x will be on a side by itself. My base is 4, and the exponent is 2. Okay, simplifying down a little bit, I have x squared plus 6x equals 16. Now, this is a quadratic, so I need to move the 16 over. Okay, so now factoring this, I see I'm going to need to use 2 and 8, and 2 will have to be negative. Got it. So solving, I get x equals 2 and x equals negative 8. All done. Now, double check, make sure everything works out well. If I substitute the 2 in up here, that's going to give me a positive number because I'm going to have 4 plus 24. We're good. Now, if I do the 8, negative 8 squared is 64, and that's going to be minus, we're still good. So always check for extraneous solutions. All right. Now, if you're good after that, you're welcome to move on, but D does have something kind of special to it. You might want to stick around and look at. All right. So looking at C, I want to solve this. I see to get the log by itself, I got to get rid of the 5 and that 7. So first off, I'm going to add the 7 to that side. So that gives me 5 log base 3 2x minus 7 equals 10. Now I'm going to divide both sides by the 5. That gives me log base 3 2x minus 7 equals 2. Now that this is isolated, I'm going to rearrange it. This is 2x minus 7 equals base 3 exponent 2. This can be simplified. 3 to the second power is 9. Now adding the 7 over, that gives me 2x equals 16. Divide by the 2, I get 8. Now to check it, if I plug 8, 2 times 8 is 16, minus 7, I still get a positive number. That's it. So hope you're finding these to be pretty straightforward. Isolate the log, rearrange it as an exponential, and then solve. Now, D, I promise to have a little something special to it. It's not that special, but I think it's pretty cool. We're going to start the same way. I want to get the natural log by itself, so I'm going to subtract the 9. So I have 6 natural log of x plus 11 equals 18. I'm going to divide by the 6, and I get 3. Now I have to rearrange it. So rearranging this one, natural log means that it's base e. So I now have x plus 11 equals e to the third power. Now, e, we can leave it as e. E to the third is just fine. Now, subtracting the 11 off, I get x equals e to the third minus 11. And that's it. That is the answer to this one. I feel so incomplete without putting that divide by 6. That's it. So you can have answers that have e in it, and that is not a problem at all. Okay, so one more page for logarithms, then we're going to move on to exponentials. All right, so again, these have logarithms in them, and there are multiple logs, but I still have terms that do not have log in it. So looking at each one, there is a term without a log. If there's a term without a log, you're going to have to change it to an exponential. All right, so looking at this first one, I don't have just a single log, so I cannot change it to an exponential yet. But I do have some log properties. I know that if I have a log plus a log, I can put the insides together. And if there's a number in front of log, I can move it to the exponent. That's stuff that we did last time. So starting off, I'm going to do the exponent first. This is log base 4 of 9x plus log base 4 of 2 to the third equals 4. Now, at this point, I know 2 to the third is 8. So this is log base 4 of 9x plus log base 4 of 8. Okay, now the addition sign means that I multiply the two insides together. And you can go ahead and multiply them if you want. I'm going to show it as an extra step to help remind you of what you should do. So now 9x times 8, that gives me log base 4 of 9 times 8. Let's see here. That's going to be 72. 72x equals 4. Okay, so at this point, I can now rearrange it because I have the log on a side by itself. So that gives me 72x equals 4 to the 4th. Okay, so 4 to the 4th, let's see here. That is going to give us 256. Now dividing both of these by 72. I have x equals, as a fraction, 32 over 9. All done. So here, we essentially did the same thing as the previous page, except we had to bring in some log properties to write them together as a single log. Other than that, wasn't anything too much different. All right, now let's take a look at the next one. For this one, I see I have a natural log minus another natural log. So subtraction means that I have to change it into division. That's the wrong color. So whatever has the negative in front goes in the denominator. So this is 4x over 7 equals 5. Now, this is now isolated, and I can rewrite it. So this is 4x over 7 equals e to the 5th power. Alrighty, so now you can do this as a single step if you want, but if fractions aren't your favorite, you can do it as a multi-step situation. I'm going to multiply both sides by the 7. That gives me 4x equals 7e to the 5th. And now divide both sides by the 4. that gives me x equals 7e to the 5th divided by 4. And that's it. Now, a moment ago, I said you can do it as a single step. What you could have done instead is multiplied by 7 over 4. Multiplying by the reciprocal will cancel out the original fraction, and you still would have got 7 over 4 e to the 5th. And that's it. That one's solved. Having e in your answer is perfectly fine, especially if you start with natural logs. All right, now for the next one. Looking right here, I have log base 6 plus log base 6. So if I have addition, that means I can multiply the two insides. So now this is log base 6 of x plus 4 times x plus 3, and that's equal to 1. I use brackets here because I didn't want too many parentheses. Okay, now that I have just a single log, I'm going to rewrite it. So this is x plus 4 times x plus 3 equals 6 to the first power. Alrighty, now this I'm going to need to distribute. I know it's tempting to try to solve and say x equals -4 and x equals -3, but it's not equal to 0. So distributing, that's going to be x squared plus 3x plus 4x plus 12 equals 6. Now combining some terms, I have x squared plus 7x. I'm going to go ahead and move the 6 over, and that's going to give me plus 6 equals 0. Got it. Now factoring, this is going to be x. Let's see here. I'm going to need to use 1 and 6. There we go. This means that x equals -1 and x equals -6. All right, don't forget you have to check your answers if you ever start with a log. So checking our answers on this, if I substitute -1 in up here, -1 plus 4, that's going to be a positive number. -1 plus 3, that's a positive number. -1 works. But -6 right here, as soon as I do -6 plus 4, that's -2. So log base 6 of -6 plus 4, that's log base 6 of -2. That's an error. That does not work for us. So my only answer here is -1. All right, let me scoot up. There you go. Okay, so hopefully that wasn't anything too crazy. Now for the last one on this page. For this one, I have log base 4 minus log base 4. I know if I have subtraction between logs, I can write it as one log with division. So right here, whatever has a negative sign goes in the denominator. So that's going to be x plus 3 divided by 2 minus x equals 1. Okay, now that it's a single log, I can rewrite it. That's x plus 3 divided by 2 minus x equals 4 to the first power. All right, now I know 4 to the first power is 1, but just to kind of rewrite it to be neat, here we go. Now, hopefully you remember when you're solving a rational like this, you need to clear the denominator. So I'm going to multiply by x, or 2 minus x. When I do that, I have x plus 3 equals, when I distribute, this will be 8 minus 4x. Got it. Now, combining some terms, I'm going to move the 4 over here. That's going to give me 5x. Subtract the 3, I get 5. And now I have x equals 1. Okay, now checking this one. 1 plus 3 is 4. We're positive. 2 minus 1, that's a positive number. We're good. So that is our final answer. All right, so we have seen 3 different type of logarithmic equations. If they have the same base, you can set the insides equal. If you have terms that don't have a log, then you need to either isolate the log or combine them, then rewrite it as an exponential. Okay, that's it for solving log equations. Now let's go over to exponentials. Okay, so to start with exponentials, we're going to do something we have already done. When we did our exponential function lesson, we talked about how you can solve certain type of exponential equations. I just figured it wouldn't hurt to talk about them again, just kind of keep it fresh on your brain. So the first type we're going to do is solving exponential equations that have common bases. Now, as we learned before, if I have an exponential equal to another exponential, as long as the bases are the exact same, we can set the exponents equal to each other. But what's important here is the bases are the same. If they're not the same, some special stuff has to happen. All right, now looking at our first one, at initial glance, it does not look like I had the same base. Here I have base 2, and then I have 32. Well, we know that I can try to rearrange the 32 so that it's 2 to a power. So let's try that. Now, last time I showed you 2 different ways you can go about trying to find a common base. You can do it without a calculator, and you can do it with a calculator. The calculator way is arguably the most efficient and easiest way to do it. But I want to remind you how to do it without a calculator, just in case you ever have to take a class where you don't get to use one, which that happens. So if I want to see if I can write 32 as base 2, the way we did it, we start with 32 and then make factor trees. If I want base 2, 2 is the number I divide by. So 32 divided by 2 is 16. Divide by 2 again. That gives me 2 and 8. Divide by 2 again. 2 and 4. Divide by 2 again. 2 and 2. So these are the factors of 32. I have 1, 2, 3, 4, 5. That means 32 is 2 to the 5th. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 32 can be written as 2 to the 5th power. Now, this isn't bad if it's a small number like 32 and you're using base 2. But if you have big numbers, it's not so nice. So as a reminder of how you can use your calculator to do it, especially if you have a TI, what you can do, you should go to y equals. From there, type in whatever base you're looking for. So I want base 2, so I'll leave 2. Then raise it to the x power. Once you have your base to the x power, go to your table. The number I'm looking for is 32. It's right there. That tells me that my exponent needs to be 5, exactly what we already knew. So writing this out, I know 32 is equal to 2 to the 5th. All right, writing my equation down again, I have 2 to the 3x minus 1 equals 2 to the 5th. Now, the two bases are the exact same. If the bases are the exact same, I can ignore them and set the exponents equal. Now, I'll add the 1. That gives me 3x equals 6, divide by the 3, and I get x equals 2. All done. And good news, since the domain of exponentials is all real numbers, we never have to worry about substituting this back in to see if it works, because every single number works for an exponential. All right, now let's try the next one. Here, I notice that the two bases are not the same, but always see if we can make them the same. My first step is, can I turn 125 into 625? So doing my same little trick, 125 to the x power, 625 does not show up. So that's not going to work. But my next suggestion is, look for a small number that can divide both. if you can divide both, it might be the base for them. So a small number that I see right off the bat that can divide both is 5. Remember, if your number ends in 5 or 0, it can be divided by 5. So going right here, I'll put in 5 to the x power. Typing it in, I see that I have 125 and 625. They both show up. So that tells me that 125 is 5 to the third, and 625 is 5 to the fourth. Doing the calculator method was much more efficient in this situation. Okay, now we can write it out again. Instead of 125, I'm going to have 5 to the third, but this one already had an exponent on it, so I have to make sure I put parentheses and then 2x minus 4 equals, here I'm going to have 5 to the fourth. I have to put parentheses because it already had an exponent on it. Now at this point, we know there's an exponent property that says if I have an exponent on top of another exponent, I have to multiply. That's going to be very important. But before I do that, I see the base is the same. It's both base 5. So I'm going to go ahead and write these down. Ignoring the base, I have 3 times, because of that property, 2x minus 4 equals, here it's 4 times x minus 3. So exponent on top of exponent means multiplication. You have to multiply the entire thing. If it helps you, cover up the base and you'll see that it's 3 parentheses 2x minus 4, exactly what we have. Now at this point, all I have to do is distribute. That's going to be 6x minus 12 equals 4x minus 12. Now solving it, I'll move the 4x over. That gives me 2x. I'll add the 12. That gives me 0. Divide by the 2, and I get 0. That's our answer. Nothing else to do. So far we've seen that if the bases don't look like they're the same, you can try to rewrite it so that they are the same. Sometimes that works, and if it does, great, we know what to do. If it doesn't, we'll cover that on the next page. But next thing we're going to do is we are going to look at 2 more problems, and these are a little bit more involved because we have to bring in more exponential properties. So looking at this one, I see that the base that I need is e. Base e, base e, that one has an e. We need to try to rearrange it. Well, this side, the left one, that's perfect. It's the golden child. Nothing needs to happen over here. So I have e to the 2x minus 1 power equals, this one is problematic because the e is in the denominator. But we have an exponent property that says that if I have it in the denominator, I can rewrite it out of the denominator if I make the exponent negative. So right here, to flip this e out of the denominator, I make the 3x negative. Got it. The next one, right here, if I have an exponent on top of another exponent, that means I multiply them together. So this is going to be times e to the negative 4x. Got it. Okay, now we're almost where we need to be. I have exponential equals 2 exponentials. Our property only works if there's a single exponential, so we need to put these 2 together. Luckily, we have another exponent property that says if you have the same bases multiplied together, you add the exponents. So this is e to the 2x minus 1 equals e to the negative 3x plus negative 4x. I understand you could have put those together already, but I want to remind you what the property is. This is e to the 2x minus 1 equals e to the negative 7x. Now I have the same base on each side, so I can set the 2 exponents equal. Solving this one, I'll add the 7 over. That gives me 9x. I'll move the 1 over, divide by the 9, and I get x equals 1/9. And we are done. There's nothing else to do on this one. Okie dokie. So now for the last one on this page. And this one is going to bring in one extra property that one didn't have. Okay, so this one automatically the bases are all over the place. We have 1/2, we have 8, we have 2. But if I look close enough, I see something very common. This is base 2. This one has a 2 also. And 8 can be rewritten as 2 to the third. So I know I can rearrange all of these so that they are base 2. All right, so starting on this one, I know if I have a fraction, I can take it out of the denominator by making the exponent negative. There's a 1 right there, so I can turn that into -1. And it still has x minus 5 on top of it. Equals, here I know 8 is 2 to the third, and it has an x on top, times 2 to the x squared. Okay, now that they're all base 2, I just need to kind of simplify down a little. Now right here, if you want to distribute the -1 to here, go for it. I'm going to wait towards the end, but if you want to go ahead and do this, I have no problem with that. That's 2 to the -1 to the x minus 5 equals, I need to put these together. So exponent on exponent means multiply. That's going to be 2 to the 3x power times 2 to the x squared. Same bases multiply together means that I am now going to add those two exponents. So that's going to be 2 to the x squared plus 3x power. I add those two together. Now, base 2, so this is -1 times x minus 5 equals x squared plus 3x. At this point, I'll distribute. That's -x plus 5 equals x squared plus 3x. This one's quadratic, so I need to move them over. That's going to be 0 equals x squared. That's going to give me 4x, and that's going to give me -5. Factoring it. Let's see here. 1 and 5 are the only numbers that I can use. Since my 4 is positive, that tells me that the 5 needs to be positive. So -1 plus 5. My answers are x equals 1 and x equals -5. So this one had quite a few properties that we had to use, but they are properties that we know, that we have used before, and should hopefully by this point be pretty comfortable using. All right, so that's it for our little review on something we've already done, exponentials with a common base. Now let's look and see what happens if your exponentials cannot have a common base. All right, so looking at this one, I want you to notice for all of these, I have exponentials still. I also started bringing in some extra stuff into it. That won't be anything hard because we know how to handle isolation. But we are going to wind up having stuff that does not have a common base. But you'll kind of get a better grasp on that by the time we work the first problem. So on these, our very first step is isolate the exponential part. Now the exponential part is whichever one has the exponent. So looking right here, I see the exponents on this 4. That means 4 is the base. This is the exponential part. It needs to be alone. That means that 6 has got to go. Divide both sides by 6. I now have 4 to the 3x power equals 5. The exponential part is now on a side by itself. The reason that's important to us is once I see this, my base is 4, over here that's 5, I can check to see if I can find a common base. Unfortunately, there's no way I can turn this 4 into a 5. And if I look for a number that divides both, the only number I get is 1. So there is absolutely no way I can make these two have a common base. Well, if fear not, we can still work this out. What we're going to do is we are going to change the exponential to a logarithmic form. And to do that, we have our handy little conversion right here. So I see, starting with an exponential going to log, the exponent, x, will now be on a side by itself. So 3x will be on a side by itself. It will be equal to a log. The base of the log will be the base of the exponent. So this would be log base 4 of whatever the exponential is equal to is inside the log. Now, easy way to kind of look at this, remember, the exponent stays on the same side. What it's equal to is on the inside. So they stay together. The only thing that changed is the log, or the base, went to the bottom of the log. Those stayed on the same side. Base went to the bottom. Now, this right here, this is a number. Log base 4 of 5, if you were to type it into a calculator, it would give you a number. We're not going to change it to a decimal. We're just going to leave it as is. So the last thing to do is divide everything by 3 so I can get x by itself. Doing that, I have x equals. Some books might want you to leave it like this, log base 4 of 5, all divided by 3, and that's a perfectly acceptable answer. To make it look a little more similar to what we've been doing, I'm going to turn that into a fraction so that it looks like this. 1/3 log base 4 of 5. This is a true statement. Dividing, that's the fraction. And this looks a little bit neater, and it's something that you would see more often because once I see it like this, I see I can turn this 1/3 into an exponent. So this is the proper form that I would like to see. But on your homework, if it shows you to do it this way, that's still perfectly correct if you leave it as a big fraction. That's it. That's all you do. Isolate the exponential, change it to a log, solve for x. Okay, moving on to the next one. Here, I see that the exponential part is 10 to the 2x power. So this needs to stay together. Everything is not that. The 4 and the 1 has to go. So I'm going to start by moving the 1. So I have 4 times 10 to the 2x power equals 20. Next thing I'm going to do is I'm going to divide both sides by 4. Doing that, I now have 10 to the 2x equals 5. Now that the exponential part's on a side by itself, I'm going to change it over to log. Doing our conversion, I know 2x will be on a side by itself equals log. The base for this is the base here, so log base 10. We remember base 10 just means that it's log by itself, so I'm not going to put a number. The inside is 5. Last thing to do is to divide by that 2 to get rid of it. That gives me x equals 1/2 log 5. And we are done. Nothing else to do on that one. Okay, so moving on to the next one. These are going to be all very similar. Starting right here, I see that the exponential part is 2 to the x plus 6 power. That means that 5 needs to go. So dividing both sides by the 5, I now have 2 to the x plus 6 equals 7. Rearranging it, this is going to be x plus 6 equals log base 2 of 7. Now the only thing left to go is this 6. I'm going to subtract it off. I know it's very tempting to try to subtract that 6 from the 7, but remember, the parentheses means that that is locked in. Nothing goes in or out. So when I write my answer, I have x equals log base 2 of 7 minus 6 behind it. You just leave it like that. Nothing else to do. Okay, now for the last one. identify the exponential part. I see my base is e, but the exponent's 2x plus 1. So that means this 3 and the 2 need to go. So I have 3 e to the 2x plus 1 equals 12. Divide both sides by the 3. That gives me e to the 2x plus 1 equals 4. Now that the exponential part's isolated, I'm going to change it over to a log. The base of this log will be e. We know that's special. Base e means natural log. So switching it over, I know this is 2x plus 1 equals natural log of 4. All right, next thing to go is the 1. So I have 2x equals natural log of 4 minus 1. And finally, divide everything by the 2. I'll be perfectly honest, right here, I'm going to be a bit lazy. Instead of writing 1/2 natural log 4 minus 1/2, I'm going to leave it as one big fraction. I told you it's an acceptable answer. And whenever there's multiple stuff there, it's fine. That's it. That's all you have to do for solving ones like this. Now, I know at this point, like, okay, cool, everything's done. Every single one of these problems only had a single exponential. So if you have a single exponential, these are very straightforward and very easy. But we've already seen that sometimes you get problems that have an exponential on both sides. Well, having an exponential on both sides gets a little bit trickier, and that's what we're about to do. And it's the last thing we'll cover. All right. So I recommend on this page, write a little small because these get a little long. They're not hard, but they are a little long. All right. Looking at the very first one, I have 3 to the 3x power equals 6 to the 2x minus 4 power. Now again, always start the same way. Are the bases the same? Here, no. Is there a way I can make them the same? Well, let's see if I can find something. 3 is the only number I can do to divide both. So 3 to the x. 6 does not show up. So I cannot change that 6 into base 3. So something's going to have to be a little bit different here. Well, what we are going to do is we are going to use that very first property we talked about for logarithms. So going back, I see that log base a of m is equal to log base a of n if m equals n. Going backwards, if I have two things that are equal, I can do the log on both sides and it's still equal. Now that might not make a whole lot of sense yet, but once I write it down, it should be a little clearer. Now here, the log that you use is arbitrary. You get to use whichever one you want. The easiest thing to do is just use natural log. It's the least amount of writing, and since these get a little long, the less you have to write, the better. So what I'm going to do is I'm going to take the natural log of both sides. So this is going to be natural log 3 to the 3x power equals natural log 6 to the 2x minus 4 power. Now, I told you this would be a little bit clearer once I wrote it down. We know from our very first page, if the logs are the same, the insides are the same. Natural log, so I can set the two insides equal. I just made a mathematically true statement. Now at this point, I'm kind of hoping that you're curious, why would I bother doing this? I just made it look even uglier. The reason we take do the log on both sides is because I know the log lets me take the exponent out front. So doing that, I now have 3x times natural log of 3 equals 2x minus 4 times natural log of 6. And yes, I understand that does look ugly still, but this problem is not going to look pretty at all, ever. But we have just made this a lot more useful. Our x's are no longer in the exponent. That's what we want. So by doing the natural log, I took the exponent out of the exponent. Okay, so at this point, I see that I have multiplication. I can distribute that natural log of 6. So this is 3x times natural log of 3 equals 2x natural log of 6 minus 4 natural log of 6. Now at this point, you need to remember, where are we going? My goal is to solve for x. I want x on a side by itself. Knowing I want x by itself, I need to get anything with the x together. So I'm going to move this term over here. That's 3x natural log of 3 minus 2x natural log of 6 equals negative 4 natural log of 6. Okay, now we're almost done. Both terms on this side have an x, so that means I can factor an x out. Factoring x out, that gives me 3 natural log of 3 minus 2 natural log of 6, close parentheses, minus 4 natural log of 6. We're almost done. To get x by itself, I just need to divide by this. So dividing by 3 natural log of 3 minus 2 natural log of 6 on both sides. I now have my answer. That will cancel out, and I get x equals this nastiness. So I'm going to write the denominator first so I can space it out correctly. 3 natural log of 3 minus 2 natural log of 6, all divided by negative 4 natural log of 6. That is our final answer. And we're done. Now, that might seem like a really long problem. That's because it is. I'm not going to sugarcoat it. This one was not the prettiest. But one reason it looks so long is because we had to write natural log so many times. I want you to think about all the steps that went into it. Step 1, take the natural log of both sides. Step 2, bring the exponent down. Step 3, distribute if you need to. Step 4, combine terms to one side. So everything with the x on one side. What's that? 1, 2, 3, 4. Step 5, factor out the x. Step 6, divide by the remaining portion, and you get your answer. So there were 6 steps to this, but it was all pretty basic algebra. So don't let all the extra stuff throw you. All right, so there's 3 more of these. So I highly recommend you watch at least one more. But if you're shaky on this, there's 3 examples for you to look at. Take a look at the next one. 5 and 11. The bases are not the same, and there's not going to be a way at all for me to make them the same. So to start this out, I have natural log 5 to the 5x plus 7 power equals natural log of 11 to the 2x power. Okay, doing the natural log means I can take my exponent out front. So that is parentheses 5x plus 7 times natural log of 5 equals 2x natural log of 11. Got it. So took the natural log, brought the exponent down. Next step, we distribute where we can. This natural log 5 gets distributed over. So this is 5x times natural log of 5 plus 7 times natural log of 5 equals 2x natural log of 11. Okay, Next step, we want to get everything with an x over to the same side and everything that does not have an x to the other side. So I'll move this one over. That's going to give me 5x natural log of 5 minus 2x natural log of 11. Now this 7 natural log of 5 is going to go over here. So that's negative 7 natural log of 11. Next thing, I'm going to factor out the x. Factoring it out, that gives me 5 natural log of 5 minus 2 natural log of 11 equals negative 7 natural log of 11. My last step, I'm going to divide both sides by the parentheses. 5 natural log of 5 minus 2 natural log of 11. 5 natural log of 5 minus 2 natural log of 11. Now I get x equals, writing the denominator first so I can space it out correctly, 5 natural log of 5 minus 2 natural log of 11 divided by negative 7 natural log of 11. And that's it. We are done with that one. So hopefully the second time you saw it, you saw that every single step was the exact same. Were there plenty of them? Yes. Were they terrible? No, I don't think so. All right, so if you're good after that, you're good to go. But if you want to see a couple more, here we go. All right, so looking at this, always start the same way. Can I make them be the same base? 7 and 10, unfortunately not. I cannot, and there's no number other than one that divides both. So I'm going to have to use the natural log method. So starting off as usual, I have natural log 7 to the 4x plus 1 equals natural log 10 to the 2x minus 1. Okay, we do that so that we can take the exponent out front. So now I have 4x plus 1 times natural log of 7 equals 2x minus 1 times natural log of 10. Okay, next step, we distribute. That's going to be 4x times natural log of 7 plus 1 times natural log of 7, it's just natural log of 7, equals 2x natural log of 10 minus 1 times natural log of 10, it's just natural log of 10. Got it. Now, combining terms to the correct side, x's are going to come over here. So this is 4x natural log of 7 minus 2x natural log of 10 equals, I'm going to move the 7 over. That's negative natural log of 7 minus natural log of 10. Factor out your x. So that's x, 4 natural log of 7 minus 2 natural log of 10 equals negative natural log of 7 minus natural log of 10. Last step, divide by the parentheses. 4 natural log of 7 minus 2 natural log of 10. And we have our final answer. X equals negative natural log of 7 minus natural log of 10, all divided by 4 natural log of 7 minus 2 natural log of 10. That's the final answer. Okay, so hopefully that's good enough. I am going to do the other one, though I don't particularly want to at the moment. I'm going to show one more example, but if you are good to go, feel free to go. All right, last one. We can do this. 2 and 5, they are not the same base. I cannot make them be the same base. So natural log method it is. It's going to be natural log 2 to the x minus 1 equals natural log 5 to the 2x plus 3. Okay, now I'll take down my exponent. That's going to be 2x minus 1 times natural log of 2 equals 2x plus 3 times natural log of 5. Next step, distribute 2x natural log of 2 minus natural log of 2 equals 2x natural log of 5 plus 3 natural log of 5. Next step, put terms on the correct side. Putting stuff on the right side, I have 2x natural log of 2 minus 2x natural log of 5. Add that natural log over, so natural log of 2 plus 3 natural log of 5. Factor out the x. That's 2 natural log of 2. Oops, I knew I had something extra. That 2 didn't need to be there. My bad. Yeah, I messed up. I brought that 2 over. I knew something was wonky on this one. There we go. Minus 2 natural log of 5 equals natural log of 2 plus 3 natural log of 5. Now we're going to divide natural log 2 minus 2 natural log of 5. Okay, and our final answer, x equals natural log 2 plus 3 natural log 5, all divided by natural log 2 minus 2 natural log of 5. And apart from that one little slip up, we're done. Okay, so obviously I saved the best for last. You now should be fully prepped on how to solve almost every exponential equation that gets thrown at you. If you have any questions about how to solve any of these exponential or logarithmic equations, please feel free to reach out. I'm always happy to help you out. But other than that, have a great rest of your day.